Well, thanks everyone for coming. I'm Michael Heemskerk. I'm architect for Stash, and today I'll be talking a little bit about data center, what it means for plugin developers, how you'll need to update your plugins to be able to work correctly in a data center installation. And hopefully I'll be able to convince you guys that it's really not all that hard and terribly involved to get your add-on in shape for data center. So with that, let's get going. First of all, let's start by looking what the differences are between a standard standalone installation and a clustered data center installation. So here you can see what a standard standalone installation looks like. It's basically just a single server with your favorite Atlassian Java app running on it. So let's say this is a JIRA server. It's got a database that it's connected to, and it's got a home directory where all of the files are stored that the application uses. So those are things like log files, temp files, but also just application artifacts such as avatar images and whatever the application stores. So when we move to a data center installation, things are a little bit different, but it still looks familiar. So here you see we've got 3 nodes now. So that means you've got 3 different servers, all running a separate JVM with the application on top of it. We still have the single database, so all of the servers are still connected to the same database. But the home directory layout is a little bit different now. So instead of just having a single home, there's actually now a local home part and a shared home part. And the local home part is just a part that's different for each of the nodes, and that will contain the node-specific files, such as the log files, your temp files, your cache files, that kind of stuff. The shared home is actually the part that's shared between the nodes, and that's typically implemented as an NFS volume or something like that. And that part contains all the application data that needs to be synchronized between the nodes. So for JIRA, those could be things like avatar images. For Stash, that will also include all the Git repositories. So all those bits of data, application data, that you need to store potentially with your plugin as well, you need to make sure that that's actually stored in the shared home part instead of just the standard home. So that's what's changing. Not terribly involved, right? But there are a couple of challenges, and they're mostly caused by the switch from a single JVM to now having multiple JVMs, and some things change. So let's have a look. Caches or in-memory state are probably going to be the biggest issue that you'll encounter. It's in our internal work when we switched over to data center, this was the place where we spend most of our time. The problem here is that where you used to have an in-memory cache or some kind of counter or a volatile variable that you were using, and you can control when that gets updated. And that works fine in a single JVM, but now that you have multiple JVMs, some of those updates are only happening on one node, and nodes can drift apart. So you need to do a bit of extra work to make sure that all of those nodes stay in sync. Where you get some really weird behavior in the application, so the user might visit the page on one node, see the data in some state, and on a different node they'll see that same information in a different state. And that can be a bit annoying, or it can really be incorrect and cause big issues down the track. So that's probably going to be the biggest issue. Next up is synchronization. Again, just switching from one JVM to multiple JVMs. So your synchronized keyword or your locks or your barriers that you're using in your code to control concurrency, they're not going to hold up in the same way. They'll still work in the single JVM, but when you switch to multiple JVMs, your operations might now suddenly be running concurrently where you weren't expecting that yet. For some cases, it's not an issue because it's fine as long as you only run that operation once per node, but in other cases, it might cause problems. So events is another area where you need to be careful. Events are raised by all Atlassian applications, and they provide a really useful integration point. You add your event listeners to process those events and do whatever you want to do in your application. But with a data center installation, you need to understand that those events are only triggered on the node where that request, the trigger, is actually processed. So say somebody creates a new project in JIRA, you'll get this project created event. That'll get raised only on the node where that request was processed. And for many use cases, that's fine, but it depends a little bit on what you're doing in your event handler. So say you're sending out an email, or you're doing a database update, it's all good. But if you're doing something else that triggers reconfiguration of some in-memory state, then suddenly it's annoying that it only happens on one node, and the other nodes never saw that event and never got the trigger to reload some configuration. So that's another area. Scheduling is the final part. So in a cluster, suddenly you have multiple nodes, and what happens to your scheduled jobs? Do you actually want them to run on each node, or do you want your schedule to run in such a way that the job runs once an hour, say, but you only want to run it on one node, and you don't really care which node? So data center means that you need to think about that and make some different choices there. Those are kind of the problem areas in a nutshell. Well, might look difficult, right? It might be quite involved. The good news is that it's actually not too hard if you don't have any of these problems. Then it's just this. This is all that you need to do. So if you don't have any caches, because you've written that stateless application that everyone dreams of, you're not doing scheduled tasks, you're not doing any synchronization, then you only need to add a single line of XML to your plugin descriptor, and you're good to go. It's just saying, well, okay, I'm Atlassian data center compatible, and that'll be enough for Marketplace to add that little data center compatible lozenge to your add-on, and the people installing it will also see in UPM that your plugin is data center compatible. So that's all you need to do, right? Except in the real world, many of us actually use caches and need caches and do some of those other things. So let's go over some of the patterns and the things that you can do in your application to make it work. So let's start by caching, because that's the most painful one that we've seen. So simplest solution for some definition of simple would be to just not cache. And it's actually a serious consideration, because in a clustered environment, if you want to keep the cache in sync between different nodes, that means that cache operations become more costly anyway, because when you add something to the cache and you need to synchronize that between the nodes, that means that now you suddenly have this remote operation that needs to happen, and there's a cost involved. So the cost-benefit trade-off of a cache changes it a little bit. And you might be better off optimizing your SQL, or adding an index, or refactoring your schema a little bit to make some of those queries more efficient. If you can't do that, then there's kind of a middle ground solution that you could go for. You could consider things like request level caching, where for each request you load the information once, and instead of hitting the cache multiple times for that request, you just use that in-memory cache or the data that you've loaded once, and you use that for the duration of the request. That means that you won't see any updates that happen on other nodes while that request is going, but for many use cases, you don't really care. That information for the duration of the request is good enough. If none of that works, then we've come up with a framework, an abstraction that's called Atlassian Cache, and that allows you to create cluster coherent and cluster aware caches that keep in sync across the cluster. So let's have a look at what that API looks like. So the cache factory is actually the entry point into the Atlassian Cache APIs. It is the factory that you use to obtain a cache or a cached reference. That cache or cached reference that you obtain will be cluster aware, and you can configure all kinds of aspects of its behavior. So let's start with cache, because it's the most commonly used one. A cache is very similar in shape to a concurrent map. It has the put and get operations, remove operations, but also the put if absent and the replace operations that we know from concurrent map. It's a little bit stripped down. It doesn't support all of the methods and all of the functionality, just because some of the functionality is quite costly to implement in a distributed environment. So it's kind of a trimmed down concurrent map, you could say. The cached reference is sort of a specialization of that. It's basically just a cache of a single object, and you would use that to load a configuration or construct an expensive object, and you want to do that only once, and occasionally when you need to rebuild it because of some configuration change. So when you create your cache, with the cache factory, you can customize the behavior of that cache using the cache loader and cache settings. So those of you who have worked with Guava's caches will probably know the concept of a cache loader. It's basically a callback that you provide, and the cache will call that whenever someone tries to access information from that cache and the information is not available. And at that point, the callback, the cache loader will get a call from the cache to load that value. That will be stored in the cache and then returned to the user. And that's a really nice way of having a cache without having to worry about all the troubles of updating that cache and checking whether the cache hasn't been updated concurrently while you were calculating the value and handling all those cases. The cache loader, in combination with the cache, just takes care of that. You can just get a value from the cache and trust that you'll get the value and it'll be the correct value. Now, the cache settings, you provide that at construction time as well, and you can use that to configure the cache, so the maximum number of items in the cache, but also time to live, and more importantly, the type of replication that you want to have for your cache across the cluster. And I'll get back to that in a bit. The cache listener is the final bit, and that's something that you can attach to your cache, and it will receive callbacks whenever that cache is updated anywhere in the cluster. So if you have an update on node 1, the cache listeners on the other nodes will also receive those callbacks that something has changed. And you can have side effects that you trigger off of that. OK. So let's have a look at the types of caches that you can create. The first and simplest type of cache is just a local cache. They're not synchronized across the network, and this is just so that you can use the same API to create local caches if you need them. They're basically very similar to Guava caches. So it's just a map that you can use. So next up is the remote cache, the fully replicated remote cache. And in this model, you have the cache on each of the nodes is kept in sync. And when somebody makes a change to the cache on one node, that change will get replicated over to all of the other nodes. And as a result, they'll be in sync. You can choose 2 replication modes here. You can choose synchronous replication. And that means that if you make a change to the cache, so say you're adding an entry to the cache on one node, then that call to the cache will block until that change has been replicated across the cluster and has been synced everywhere. And that gives you strong concurrency. It also means that your request is actually waiting until that remote call completes. And it can be a little bit slow, and depending on the type of information that you're storing in cache and how you're using it, you might not need that strong consistency. And then you can opt for asynchronous replication, and that just means you make your change on, let's say, node 2, you add an entry, and the method returns the moment that those replication calls have gone out, but it doesn't wait until it gets confirmation that it's been replicated everywhere. That means that you get a little bit of a delay, but you still get consistency eventually, and usually you're talking milliseconds instead of, let's say, seconds or minutes. So it's still consistent and still does conflict resolution if there's a conflict, but it will give you a bit better performance. So those are the 2 main types. And then there's a third type, which we call a hybrid cache. And this is kind of an interesting mix. So in this model, the caches are local, and each cache on each node will have its own contents. But when an entry from one cache is removed or updated on one node, it sends an invalidation to the other nodes to basically signal to the other nodes, say, hey, this value has changed. Whatever value you currently have in the cache, it's probably not valid anymore. And this cache is useful in a couple of situations. One is when, for some reason, you don't want to synchronize the cache values across the cluster. And that can happen when you need to store objects in the cache that are not serializable, for instance. So in that case, you just can't. It's all over. And another reason might be that it's a really big, expensive object that you don't want to serialize over the network because it's going to be slow and costly and eat up a lot of bandwidth. When you use a hybrid cache, you really need to add a cache loader to that, where you can get some really weird results. You can get a kind of ping-pong behavior where you update the cache on one node, that triggers an invalidation on the other node, then a process on the other node tries to access the same value, sees, hey, the value isn't there, I'm going to load it, I'm going to put it in the cache, and that triggers invalidation on the other node again, and as a result, your cache gets invalidated all the time. But if you provide a cache loader, then Atlassian Cache will detect that there's a kind of predictable way of getting the value, and it will just load the value and say, okay, I assume that the value that I'm getting now is actually valid for the current version of the cache, and it won't send those invalidation triggers. So hybrid cache in combination with a cache loader works quite well. So enough talk about the theory. Let's have a look at a bit of an example that I've prepared. So here I've got a service that's part of a JIRA plugin, and what the plugin does, it provides a little bit of a small panel on the issue, and it just shows you who's actually looking at that JIRA issue at this time. It's a bit of a contrived example, and if you would do it for real, you probably wouldn't do this on top of Atlassian Cache. You might just use the database for it, but for illustration purposes, this is how I've done it. Conceptually, what it's doing is it wants to maintain a single cache, a mapping of, given an issue key, the set of users that are actually looking at that cache. Now, there is a problem, and the problem is that the application user, JIRA's application user, is not serializable. So we can't just have a remote cache and have that synchronized. So I'm actually creating two caches here. One is a cache of the issue key to the set of user keys, just plain strings, to identify the users that are actually looking at it. And then there's a secondary cache to resolve that user key into a full-fledged application user object. So let's have a look at how you use the cache factory to create these caches. So the first one that I'm creating here, yeah, that works, is the user cache. So that's given a user key, I'm getting an application user. So you create the cache by providing the cache name. And that cache name is important because that means that if other nodes or other classes get the same cache, or the cache with the same name, they will also see all the values in that cache across the cluster. I'm providing a cache loader here, and there are some cache settings that I'm also providing. In this case, I'm saying it's a remote cache, but I'm replicating via invalidation. So this is the hybrid cache. It's not replicating the values, it's only replicating the invalidation triggers. And I'm putting an expiry on this of 10 minutes to say, well, just in case a user updates his avatar, eventually I want this to update. So after 10 minutes, I'll just reload that user object again. So the second cache, that is defined up here. So that's given the issue key, I'm just storing a set of strings of the users that are currently looking at it. Again, a username. I'm not providing a cache loader here because I really can't. It's not stored in a database. This is the functionality that my application provides. And here I'm providing a cache settings builder. And I'm saying this is a remote cache. I'm replicating via copy. So this is a fully replicated cache. And I'm setting an expiry here, an idle timeout of 30 minutes, with the idea is that if nobody's looking at who's looking at a particular issue, that means that nobody's looking at that issue, and I can just clean up after 30 minutes. This is just a bit of cleanup. So this is how you construct the caches. I'll briefly show a bit of the code on what you actually how you actually use the cache. So let me scroll down a little bit. Oh, not too far. OK. So the methods that you see here, I won't go in all of in all detail here, but basically I'm using the get method here, the get method. I'm using a put if absent here, and those are just the well-known methods from concurrent map. Let me just go down a little bit further. Yep. OK. So here is an example of how you typically update one of these caches. And it's the same pattern that you would use with a concurrent map. In a loop, I'm checking, I'm first loading the cache entry. I'm checking whether it's up to date or whether I need to update it. And then if I need to update it, in this case, it doesn't exist. So I'm putting in a new collection here. And I need to check whether between the time that I retrieved it and I'm trying to update it, whether another thread or another node actually has modified the cache. So you need to track that update here, and here there's a replace call that basically does the same, but it's an update. And this will only update if the current value is viewers, and that's the value that I retrieved previously. And this is in a while loop to make sure that if something has changed, OK, I'll just retry the logic and try to add it again. And that's how you'd use it. But if you use a cache loader, then you don't need to do any of this messy stuff. And the code becomes quite nice. You just do a get, and it'll load the value for you and put it in the cache. So that's Atlassian cache, and that's probably the most important of the frameworks that we provide. So synchronization is the next issue that I discussed. Again, if you can avoid it, if you can avoid using locks, then you're probably in the best place in terms of scaling. And that's one of the things that you also need to consider in a data center installation. You're typically dealing with more users, more projects, more issues, more repositories, bigger repositories, and all of that. So if you can avoid using locks in those cases, that will be helpful. But if you can't refactor your code to make it completely lock-free, then perhaps you can switch some of the locking that you do to optimistic locking in a database and still avoid having to do the lock all the time and just have the retry behavior if there was a concurrent change and you detected that in the database. But if you can't do any of that and you really need to take out a lock that's cluster aware, that locks a cluster, you can use Atlassian Beehive, which is a really simple API, and this is the whole API demonstrated in a single example. So you see there's a cluster lock service. You use that to obtain a lock, and the lock that you get here is of type cluster lock, but it's really just a standard Java concurrent lock. And you can do the well-known operations such as lock, and then you do your expensive operation or your protected operation in the trial block, and finally you unlock again. You can also do things like try lock and whatever you are familiar with from the lock interface. Word of warning, again, in a cluster, try to avoid this if you can, because it can really introduce an artificial bottleneck, and you can end up with lots of requests ganging up, waiting to obtain the lock, and it'll hurt your scalability. If you do need to use a lock, try to limit the scope of that lock. So if you've got this operation and you need to ensure that it only runs once for a particular issue or once for a particular repository or something, then you can use this name to kind of reduce the scope of that lock. If you include the issue ID or the repository or project key in here, and only locks looking for the same scope will actually be affected. So that's that. Event handling. So as discussed, events are only local to the node where the event is triggered. And sometimes you need to do node-to-node coordination to make sure that some side effect actually happens on each of the nodes. There are a couple of solutions that you can go for. One is to use Atlassian cache and either use the cache loader to also trigger some side effect. You can do that when you've got a configuration object that you just retrieve for each request, and when that gets invalidated, it's reloaded, and you can do the side effects. Or you can use cached listeners to get a callback whenever there's an invalidation somewhere, and then you can trigger your side effect. And finally, you can use product-specific APIs to do node-to-node communications. And unfortunately, we don't have a cross-product API for that yet, but it is something that we're considering. So that's event handling. The final part is scheduling, and that is really a little bit different in a cluster. So we've come up with a framework called Atlassian Scheduler, which allows you to schedule jobs and make use of the cluster capabilities as well. So this allows you to schedule a job either to run at a particular schedule on each of the nodes, or when the time comes to run the job, to just pick one of the nodes and have it execute there. And it depends on your use case, on which mode you want, but this allows you to choose. So just briefly, the schedule service is your entry point into the API. And then when it comes to running the job, there are actually two aspects there. So you've got the part that actually needs to run the job, that needs to understand the logic and execute the job, that actually sends an email or whatever it needs to do. And then there's the configuration, and that is describing on what schedule should it run and how should it run. Should it run on particular nodes, or should it run, just pick a node and run on one node only? In Atlassian Scheduler, the job runners are all local to the node, but the configuration is synchronized across the cluster again. So when you schedule a job on one node, you're actually scheduling it for the cluster, conceptually. So let me explain how it works by an example. That's the best way. So here in the constructor, I'm injecting the scheduler service, and I've got an init method here that's called by Spring whenever the application or the plugin starts up. I'm doing two things here. So first, I'm creating a job runner, which I'll show in a bit. And that's the component that's actually capable of executing the job. And then here I'm telling the scheduler service that this node has a job runner. This is the key that I've given it, some identifier, and this is the runner. So I'm just providing the instance to Atlassian Scheduler. And this is saying to Scheduler, hey, this node is now capable of running jobs of this type. The second part here is that I'm actually going to schedule the job. So I'm giving the job that I'm scheduling an ID as well. And then I'm configuring the job. I'm saying, well, OK, this is a job of this type. I'm providing the runner key. I'm saying this should run once per cluster, which means that when it comes time to run the job, just look at all of the nodes, see which node actually have this capability, pick one of those, and run it there. You can also run each node, and when you do that, it will do the same thing. It will detect which nodes have that capability, and will just trigger the job on all of the nodes. And here I'm defining a schedule, in this case, a cron expression to run daily. So that's the part of registering a job. But what happens when it comes time to unload your plugin because this node is shutting down? There's a bit of a twist here, because when the node shuts down, it means that this node is no longer capable of running the job. So you unregister the job runner, but you shouldn't unregister the job. You shouldn't unschedule the job, because there might still be other nodes in the cluster that are still capable of running the job. And if you unschedule it here, you're unscheduling it for the cluster. So the configuration is for the cluster, and the capability is for the local node. So that's a little bit of a twist. Let me show you really quickly what the job runner looks like. It's pretty simple. Yep. So that's it. It's a really simple interface. It has just a single method, run job, and you call that to basically run the job. And here it calls out to the who's looking service and says, well, do your thing, send out that fancy report. And it either returns a failed or a success. And that information can later be retrieved from the scheduler service as well, if you want to detect whether the last run failed or succeeded. So yeah, that's the gist of it. Almost. So as I said, there are some product-specific APIs as well. So we did our best to create the cross-product APIs, and we did a pretty good job with Scheduler and with Cache and Beehive as well for some of the use cases. But when it comes to node-to-node communication, we started with the idea that we wouldn't need it, so we didn't build it cross-product, and then JIRA discovered that, hey, we've got some use cases where we need it, so they built their cluster messaging service, which allows you to send a message to a topic, and that then gets sent to all of the nodes. Confluence did a similar thing. They have their cluster event. You can add that. You can implement that interface on your events, and when you publish that event, it will actually get published on all of the nodes, so you can process it. And they also have a variant of cluster messaging service, but the name escaped me, so I didn't put it up there. And Stash, that I'm working on, it has got its topic service, which is similar to that, So that's a candidate for another API. And we've got a bucketed executor, which is a specialized executor service that uses some type of mapping to make sure that all the jobs for a particular partition end up on the same node. And that allows you to use JVM local concurrency control again. So that's just some optimizations that we've got. And that's it. You can find information about how to create the data center add-ons on developer.atlassian.com. There are some bit.ly links here. But if you just go to developer.atlassian.com, you'll find that information as well. Those documents also contain information on how you set up a test server using amps and how you can test your plugin in a cluster, in a test cluster. Then there's an Atlassian Cache 2 overview, which is quite good and quite useful. It's in the Confluence space in developer.atlassian.com. And then in Stash, we also have a kind of tailored guidelines for making your Stash application or your Stash plugin data center aware. And that's all I have. So thank you very much for coming, for listening.